Tonight's agenda is a fascinating one. We're starting off with Viktor Trón, who's going to talk us through the Ethereum Swarm platform that he's put together and built and written. And then we're going to take a short break, and we're going to go into an hour-long panel. So warning, you might want to take your comfort break at that point. We will have a panel about law and the blockchain. So we have 4 esteemed panelists introduced by Stuart Mast. Where's Stuart? Back there chatting. Okay. Thanks to Stuart for putting it all together, and we'll bring that to you now. But without any further ado, Viktor, in your own time.
Can you guys hear me? How can I? Is this going to be okay? Yeah. Okay. Sorry, I'm not sure how my medication works, so I sit down better like this. So I'm happy to talk to you here tonight about Swarm, which if Ethereum is the word computer, then Swarm is the word hard disk, so to say. Why is this important? From the very early on, the founders of Ethereum realized that Ethereum is a blockchain and is offering a decentralized consensus engine over a Turing-complete system. Is a fantastic asset, but what else can we do with it? And they soon realized that for example, we can fix the web maybe, and realize that if you complement the blockchain decentralized consensus engine with a few other services, for example, a decentralized storage layer and some sort of decentralized messaging system, then you have everything that you might need for the third web, so to say. So tonight we are not only going to talk about Swarm, the decentralized storage system, but in general maybe a vision of how Web3 experience would look like. So I would like to present tonight in 3 parts. Let's see how it spans out. In the first part, I would like to drill through very quickly some low-level details and especially offer it as a kind of finger practice of how Ethereum can serve as a fantastic platform to architect a system of incentives where participants in a community, in a network, are forced to behave according to certain rules that are conducive to the desired operation of the system. This is what I'm going to talk about in the context of Swarm incentives. In the second part, my colleague Nick Johnson is going to talk about the Ethereum name service, which bridges the gap between these low-level parts where I'm going to mention hashes and chunks and crazy things like this, connects it to the level that's meaningful to the user, basically the semantic web. I'm kind of abusing this term right now. And finally, after that, I would like to kind of expand the discussion a little bit. Maybe maybe better do it in an interactive session. I will see how it goes. But I'd like to indulge in certain, maybe fairy tale, maybe somewhat science fiction visions of what the Web3 experience could look like and what an ecosystem full of its base layer services like Swarm and Ethereum can bring, and what value it has to users. Okay, back on track. So before we go into what Swarm is, maybe a little bit of history is needed. So in the old days of the Web 1, what did you need to do if you produced content and wanted to make it accessible? Basically, you had to have a web server which you operated yourself. You had to pay for the maintenance costs, even though no one cared about your content. And if you happen to be lucky and get, say, slashdotted, or if your content became suddenly popular, look what happened. Exactly the opposite of what you expected. It's not that you became more available, but actually you got almost like DDoSed, and if somehow your server survived this, then you paid horrendous amounts for bandwidth use. And if you were less lucky, then your server crashed, and even those who were able to view it before couldn't any longer. But at those times, you had relatively extensive control over your own content. Now, the infrastructure problem of the web server maintainer was somewhat rectified in the times of Web 2, where cloud providers came up with relatively clever infrastructure that alleviated this problem and offered content providers technology that allowed them to scale according to their popularity. So they basically put clever load balancers in front of servers who took care of spinning up instances as a response to a certain content popularity. However, this came at a certain cost, and as we all know, content producers are more or less forced into what my colleague Daniel likes to call it, the Faustian bargain of content hosting, which is that as in return to this very cheap and sometimes even free services that scale and help content producers to host and serve their content to their audience, they on the way they gave up quite a bit of autonomy over the data. It's not only that it's in these centralized silos power to control the use space, but they often aggregate and collect user profile data that then they can sell on to third parties. And this kind of monetization option has a lot of negative consequences on how the web works. So how can we fix some of these problems? Quite early on, there were solutions which were based on this idea of peer-to-peer. So in these cases, the content is distributed among peers in a distributed network of nodes. And you can see that if you provide some sort of way to take care of redundancy in the network, so that certain pieces of data are replicated well enough that the dropout of certain nodes in the network don't count too much, then you have a situation where your system might end up being more resilient, more fault-tolerant, and even zero downtime, which is very rare with centralized solutions. And often you get this deal at the fraction of the cost of what you would have with centralized systems. Of course, the problem with this that some of these solutions from early on, like Napster and the like, were somewhat centralized anyway. So that led to, because they were used for activities of copyright infringement, the powers that be went after them, and most of these outlets were shut down. And ultimately, what remained is BitTorrent, which is a fantastic solution to some of these problems. However, it still has a missing ingredient, which is incentivization. Basically, it's not solved how nodes that help distribute content, so to say, seeding content, what incentivizes them to do so. And still there's a problem of content producers not very easily being able to share the costs of sharing their content with their audience, with their consumers. There's no frictionless way to do that. And so this is where Ethereum comes in, and this is where Swarm would like to make a difference. And our team was mainly concentrating on the incentive system. Is somewhat due to the fact that in the fall, when we had certain austerity problems in Ethereum, we cut certain projects' scope, and since in terms of file distribution and sharing, some other solutions already exist, notably IPFS, we concentrated more on aspects that were as yet unsolved. So the incentive system was such a focus. And that explains also why there was the first bit that we came up and wrote 2 papers about. So these are the Ethersphere orange papers, the first 2 in the series that we published. And they, in order to understand them, maybe I just quickly give an overview of how Swarm works. So from the point of view of the user, the Swarm is a document storage system and content delivery network, which offers a serverless hosting solution where you can retrieve data based on the familiar URIs. But underlyingly, what Swarm does is that it chops your data into tiny little pieces and somehow you guys also find it extremely hot here, or is it just me? Because I'm sweating like a pig. Okay, so yeah, so it might affect my brain as well a little bit. So anyway, so the storage problem is basically reduced to the problem of storing chunks over a network. All the higher level assemblage of data and linking and referencing are kind of higher level layers. Now, what happens to chunks? What happens when someone uploads content to the Swarm? How do you get data in? Oh, there. Nick, can you give me a timing? How much time I have? Just double click on it, I think it's gonna work. So let me talk. Let me talk, and then we figure out the slides next. So what happens is when we ingest a piece of file or a document, we chop it into tiny pieces, like 4 kilobyte little pieces, and send them off to the address that they belong. So what's this address business like? How come a chunk has an address? Well, an address is basically a hash of the chunk. A hash of the chunk is a digest that has the properties that is collision free, so and uniformly distributed. So if you have a large number of these chunks, you can be pretty sure that it's uniformly distributed across the address space. Now, the interesting thing is nodes who participate in the Swarm network also have addresses, which is based on the hash of their public key, which means that the nodes are immediately linked into into like payable entities, accounts on the Ethereum blockchain. So when chunks are sent out to the network, they basically enter your closest neighbor to that chunk. That's where you send it to first, and through a series of forwarding operations, the chunk will end up at its desired destination, which is at a node that's closest to that chunk address. That node is called the custodian, and that's where through routing protocols, a retriever who wants that content will find that particular chunk. So this is what it looks like. It's something better. Sorry, guys. So when we chop the data, this is the chunk tree that we end up with. This is a Merkle tree that has properties of integrity protection and allows for random access into the files, which means that, for example, you can browse, say, a certain directory path in a huge file system without downloading the whole thing, or you can skip and watch a movie from the middle without downloading the whole stuff. So this allows for all kinds of clever things. So how do you retrieve a content? It's the same way. So you basically send a retrieve request, and you send it to your neighbor that is closest to the address, and recursively all the nodes do the same. So through a series of forwarding hops, the routing algorithm guarantees that your request will end up with a custodian who will be able to serve you with the data. So the interesting thing to note here is that unlike traditional distributed hash tables, Swarm is somewhat specific in that it's not only metadata about the whereabouts of a file that's found within the closest node, but it's actually the data itself. And it has very interesting properties following from this. So I have to speed up a little bit, I guess. So far, out of? I've not been talking for half an hour, have I? Okay. Okay, so I tried to do it a little bit quicker. So we came up with this system called, somewhat playfully, swap, swear, and swindle. And the incentive system has basically two pillars. One takes care of the part of the operation that relates to smooth, low latency retrievals. This is this kind of corresponds to compensating nodes for their bandwidth and for their efforts to make low latency transport possible. On the one hand, there is a completely different problem, which relates to make sure that data is preserved, even when the data is not often accessed. So if the data is requested by a lot of nodes, then based on the bandwidth incentive, which pays nodes for serving a particular chunk, they'll be incentivized to keep it and cache it. Therefore, popular content automatically replicates across the network, and therefore serves as the incentive for the swarm to become an elastic cloud, which auto-scales to popularity. But what happens to things like my backup or my birth certificate that I really want to have in 10 years when I first want to access it, but for 10 years I'm probably never going to care, etc., etc. So for this type of files and documents, there's another incentive system that's needed, which more resembles an insurance system, whereby I buy a promise that you're going to keep a piece of data for me up to a certain time or date of expiry. And I think we should skip some of these details. So the swarm accounting protocol is just a clever way to account for the mutual use of resources when you pass content, pass chunks. So when chunks are retrieved and you answer to delivery requests, then on every live connection there's a tally that calculates, like, give and take, basically how many chunks I gave you, how many chunks you gave me. And on the long run, if we have approximately the same consumption and interest in data, then on the long run this equalizes and our balance will be approximately 0. Now if the tally tilts too much in favor of one peer, then you obviously expect some compensation, and in these cases you send a check to the other person to the other node. Checks introduce another interesting possibility. You can delay the caching of checks, which saves on transaction cost, and and therefore allows for all kinds of savings. As for the storage, the most interesting use case that we wanted to cater for is the so-called upload and disappear situation. This situation where we really want to upload content and right away settle on some sort of insurance that it's going to be stored and it's going to be available up to a certain expiry date that I want, without me ever having to be present and check on the file or download it. There's various techniques that we use for this, that include erasure coding for redundancy, proof of custody audits that check regularly the integrity of data and repair the data if certain chunks are missing, because based on the redundancy, unless there's a lot of the data is missing, it can still be recovered. And some of the details I can talk about in the question section. So the most important part is that how we use the blockchain for this. So the most interesting point is that when you enter a store request because you want to upload a certain chunk, then the node that first takes over that task, takes over the store request and accepts it from you, they respond with a receipt. That receipt is gonna entitle the owner to litigate against the swarm in case the chunk is not found. And the litigation is basically sending a challenge as a transaction to the blockchain, where and the blockchain can prove whether the proof of custody that they provide as a refutation for the challenge is correct or not. So we had to come up with ways to represent these proof of custodies in a compact way and easily verifiable from within the smart contract. And also we have to come up with ways to do the proof of custody that helps optimize the problem of proof of custody audits for erasure coded, so redundantly coded files. So these were the challenges that we tried to solve with the system that we came up with. Okay, so I think I'm gonna skip this, and since time is passing, I think I should give it over to Nick right now. Yeah. And then we come back. So Nick will talk about. You have your slide?
Right, hello. My name's Nick Johnson. I work at the Ethereum Foundation as of Monday week, but they already have my nose to the grindstone. Not that it's unpleasant talking to you all you fine folks. I'm glad I'm here. I've been working on the Ethereum name service, and this basically provides the core component that maps from computer readable and secure hashes to human readable names. My design goal in building this was to be useful for more than just a single task, much like the DNS system is used for a variety of applications. So why do we need another name service? This may be familiar to some people. And you may already be familiar with NameReg, which is a basic name service that's deployed on Ethereum. It's integrated at a basic level into Web3. And it provides basic name resolution properties. It has a few issues, though. It doesn't support delegation. So paradoxically, for a name service that's deployed on a distributed platform, it has centralized authority. There's only a single contract that can be authoritative for all names. There's a single flat global namespace with no hierarchy. Because there's a single contract, there's no support for different implementations of resolvers that might have different needs or need to resolve different sorts of names. The other problem that NameReg has is that it conflates several different areas that are important to name registration. On the one hand, you have actually looking up a name. On the other hand, you have how to register a name, which we on the internet use with registrars and so forth. And finally, you have governance, which is who decides who gets to register names, how much do they pay, how are the names handed out, how long can you keep them for, and so forth. And each of these are separate issues that need to be dealt with separately, but they're also largely orthogonal to each other. You can solve one well and leave the others to someone else. So the Ethereum name service focuses on the first step, because it's the one that needs to be agreed on widely by the greatest number of people, and it leaves the rest to future work. So what makes a good name service? In my mind, like, this is my list of criteria. You may disagree vociferously. We've been having some interesting ongoing discussions, and I'd encourage you all to join them. So separation of concerns, like I just outlined, it shouldn't try and do many things as a proposal. Eventually the system will integrate all three of those, but they need to be considered separately and on their own merits. It needs distributed authority. Unlike NameReg, you should be able to have multiple implementations. You should be able to delegate from one to the other so that you can say this particular subdomain is this service is authoritative for that. It needs support for many types of records. You shouldn't have to hard code in this can resolve swarm hashes and it can resolve names of contracts or addresses of contracts. But then if you later want to add in, say, mail exchanges or IPv4 or IPv6 addresses, it shouldn't require changes to the protocol. It doesn't need, but it's very useful if it has compatibility with existing systems. It should be possible to build gateways so that this functions elsewhere. And ideally, it should support both on-chain and off-chain resolution. So when we're resolving swarm hashes, frequently the resolver will be a web browser or some proxy server that sits between the web browser and the swarm. But in other cases, it may be a contract on the chain. And if you're doing other resolution tasks, such as looking up names of other contracts, then being able to do it cheaply and on-chain is very useful. So the ENS as a whole only has two major components. There are name services, which are on-chain. They exist as contracts, and they have a well-defined interface that everybody agrees on. And you have local resolvers, which are libraries that take part of that are part of a contract or a browser or a gateway to DNS, for instance. And resolvers talk to name servers, and name servers respond. There's no direct communication between the services. So the organization of ENS, it's inspired by DNS, but not entirely like DNS, and also by Maker's name service proposal. And they also called theirs ENS, just because we need some extra confusion. But I've since talked to them, and I think I've worn them down, and they're mostly agreed that this is a reasonable proposal. Unlike DNS, it's hierarchical, based on name components instead of based on authority delegation. So the boundaries of authority, as you'll see, are strictly according to parts of the name. And it uses relative naming, which means that you can say this entire namespace is a subtree of my namespace, which will also become apparent in a moment. Any name component can have records associated with it, which can be swarm addresses, or they can be mail exchanges, or any number of things. And I just said that. So this is an example of a simple layout of an ENS hierarchy. Down the bottom, you can see we've got a global root. And this is a consensus, really. There's nothing intrinsic to the system that says there's a single global root, but we're assuming, for the sake of argument, that this is the one most people agree on. And the global root has a single entry for .eth, and that points to the .eth root. And each box here represents a separate contract on the Ethereum blockchain. So the global root has its own contract, and it has only a single node, which contains, in this case, a pointer just to .eth. The .eth root is what we would think of as a top-level domain. It effectively is. It takes care of registration and so forth. Both of these have published public APIs for registration, well-known rules. Getting a new top-level domain in is obviously quite the involved process, because we don't want to overwhelm people with them, unlike IANA. And one person laughed, that's good. And buying a domain, for instance, and again we're getting into governance. This would also be published and well known, but hopefully a little less involved. And then so the .eth root, for instance, has entries for my site. So that's, if you're starting at the global root, that's mysite.eth, and the DAO. And each of these have their own resolvers. So up in the top left, we can see that the person who owns my site has deployed their own resolver to the blockchain. It has 3 nodes here. It knows how to resolve www and forum, and it has a root node, which is what everybody else points to as the authority for my site. And on the right here, we've got the DAO's resolver, which again is very similar, except that while they still have a record that people point to as the authority for the DAO, they also have their own root, and they have their own internal nodes. And the point of this is that while most people might point to the global root as the root, you know, much like we all agree on the root servers of the DNS, except a few very strange people, you can also develop your own root, and it can have your own mappings, and it can have the same set or a superset or a subset. And in this case, the DAO has their own internal root. It points to .eth just the same as everyone else. But for internal use, they have a .dao suffix, which only their users can resolve, and that points to some internal sites, for instance. So here we see how you'd resolve, say, www.mysite.eth. You start at the root, you ask it for eth, it points you to the .eth root, the one node in there. You ask that node for a reference to my site, and you get the root of the my site. You ask that for a reference to www, and it points you this time to another node inside the same contract. But the local resolver doesn't have to care about that, whether it's the same contract or another. And finally, your resolver asks that node, what is the IP address of what is your IP address? And it fetches the first A record, and it gets back 8.8.8.8, which would be a terrible address because that's actually Google's DNS. But anyway, I needed something short enough to fit on a slide. So here we see, for instance, how the DAO would resolve it, and the steps are exactly the same, except that we're starting at a different route, and we follow the mapping, and the mapping in this case points to the same location. And finally, how the DAO would resolve internal names. The same process is followed, but this time from a route, from a path that can only be followed if you start from their root. So hopefully I've given you a sort of a broad overview of the basic system, of why I think it's necessary, and of what it does. And I hope you're convinced that it distributes authority effectively, and that it separates concerns so that we can deploy the system, and then we can have the argument about how we're going to govern .eth, and also about how we're going to register names, and how long they'll last for, and whether we should have auctions, and so on and so forth. So this is written right now. The ENS spec is available at that URL. It's a draft, but it's fairly complete. It's had a lot of feedback. I'm pretty happy with it, at least. There's a reference name server and local resolver implementations available in Solidity. At that address, github.com/arachnid/ENS. And there's ongoing discussion. If you're interested in this, and I hope some of you are, then join us on Go Ethereum name registry. Scroll back and read some epic arguments about auctions and other Byzantine aspects of how we think we should govern the whole thing, because although I say where concerns are separated, that doesn't stop us arguing about them all at the same time. And I hope this was useful. Thank you. Please hold your questions despite the slide.
So if you don't mind, I take it back a little bit. So I hope you understand why the Ethereum name service is hugely important. It's very, very important, because that's the only way that mediates between the immutable content and the of the swarm, where hashes, basically a hash changes if you add like a bit of new information to a file, which means that they once you viewed something retrieved based on their hash, if someone changes it, it's no longer, the change is not there. So the only way you have permanence and of some semantic thing, like for example my CV, is through a name system where you always register the most current version of what you intend to be the content. And also they are extremely important because they will be entry points to certain databases which we serve as the decentralized layer for dapps. For example, you would store your posts and who likes what in your social network in these swarm databases, ideally, and therefore all these operations on these Merkle trees and that constitute the description of a key value store, like for example a routing table, or as I said, as a database. They all can be described using the same kind of structures, and since they have the Merkle property, their root hash can be registered on the blockchain, but whole states and whole databases can be easily handled off-chain, and think about them as basically side chains with their own either consensus rules, or it's just user data which where the sole arbiter of or the oracle of what the current state of the data is one user. So the most important takeaway message that I want to kind of wrap up with is that first we targeted the basic requirement from Swarm, that it does not only carry over all the properties that we know like decentralized storage solutions would have, basically zero downtime, fault tolerance, and censorship resistance, but also provide some sort of incentive layer which makes sure that it's self-sustaining in an economic way over the long term, and provides a stable architecture. So that's our research goal, and of course time will tell whether this stands up to the actual real life, and whether it works out in the wild. So currently the status of the project is we have almost done releasing the POC, that proof of concept, version 0.2. It's if it's going to be released, then we're going to open up a test network on the Ethereum modern, and probably invite developers or people interested to join our network, and try testing it with proper use cases, and with proper mass usage. There's a lot of work ahead, and we have basically planned work about for 5 years, for 10 people at least. There's a lot of interesting projects in the making. For example, we're gonna have payment channels implemented via Raiden. Hopefully that collaboration works out really well. Where Raiden Heiko Heiss is a project. They provide the payment channel implementation and the solidity contract part of a it's basically a lightning payment network and Ethereum, which scales very well, and hopefully we can help them provide the routing layer for the swap network that it needs for for chained payments. Likewise, we would like to have this database implementation running on Swarm. That is also the first step towards doing a Swarm-based light client, which is based on the idea that the whole of the blockchain, the state data, and the contract states are also stored in Swarm and only accessed on demand, the same way as a light client implementation would do. And there are various other plans in the making. I don't know how much I should talk about them right now. So maybe I should open up to questions rather, because that makes it even a bit more dynamic, because I can ramble on forever. Yes. Yeah, we are basically sister projects that like march on like for the same common goal, and like have Web3 as a success, and like bring back the ethos of the original internet, and provide open protocols that allow for frictionless interaction of individuals without necessarily having to have third parties, intermediaries in between. And in more technical level, IPFS is basically a Lego kit of Web3. So it defines protocols and abstractions over typical ingredients and components of such decentralized systems, especially related to storage and communication. So, for example, peer selection, routing, chunking, or the way these Merkle DAGs are interpreted. And most of these protocols are extremely valuable, and we planning to refactor some of the Swarm code to comply with some of these standards, but we don't necessarily want to follow the already existing IPFS modules in some of our plans. For example, in the routing protocol, we had some quite original ideas how to make it more efficient, or similarly with the manifests. That the manifests are these JSON objects that describe the routing tables, or almost like describe basically a directory structure in a serverless setting. And these manifests are very similar to what IPFS has as Merkle DAGs, and these describe these hierarchical relationships between nodes. And so we have a slightly different flavor of that than what they're using. But in general, the direction of the two projects are very similar, and we would like to synergize as much as we can. As far as I know, storage, they just launched last week. There was a launch party in Berlin, which I just sadly missed. As far as I know, they're more centralized in their solution, and I'm not sure if they actually seriously taking it as their goal to be a low latency server of interactive web applications. Because in our scenario, that's a very, very important use case, that we basically serve the web like interactive real-time applications. So we have to cater for low latency use. I'm not sure if it's Storj's plan or not. But otherwise, the systems are very, very similar, especially in terms of the way they use erasure coding and proof of custody audits is somewhat similar. If you go into the the tricky details, of course, which you're probably not concerned with, then of course there's a world of difference, but it's only a handful of people care about. So. I don't want to comment. I would like to be faster than the web now, but it's always depends on a lot of circumstances. And
like IPFS, what I understand it supplements to use so if I have like a DApp, I made a DApp actually last week, and at this moment, so contracts in Ethereum, and I serve my assets files just in S3 bucket, but you could potentially put into the IPFS. And are there any dependency between the Swarm and the Ethereum itself, or are they completely separated stuff?
yeah, so deep down, they both run on the same peer-to-peer network layer, which is called def peer-to-peer. So in that sense, Swarm is the the sister protocol of ETH, which is the Ethereum protocol. The protocol in terms of the scheme with which nodes exchange transactions, like broadcast transactions to each other, accept blocks and send blocks to each other, etc. That's the ETH protocol, and the BZ protocol is the protocol of Swarm. That's what the bees speak between each other. that runs on the same multi-protocol network layer called def peer-to-peer. That's what holds them, kind of binds them together. And actually, this is a very important point, just to emphasize it. What we really have here is a fantastic opportunity to so with Swarm, and especially in a context where you have a web browser or a mobile client, where Swarm basically is just a backend to browsing behavior. So when you visit links, you follow from one link to the other. In these cases, the synergy between a decentralized storage solution and the blockchain is really incredible. So we can finally formalize and link certain browsing behaviors to contractual relationships and agreements. So if you're part of, say, an opt-in community where you say that each time you visit a media file, let's say Imogen Heap's song and like an MP3, then you check whether the smart contract that's triggered by you playing that song is verified, is according to your principles. It represents the ethos of fair trade music, let's say, and you know exactly that when you click yes to the question of yes, do you want to pay per play for this song, then you know exactly that your money will be distributed to the rightful owners of that license to that song. So the smart contract somehow described in an accurate and transparent way the content producers wish how they should be remunerated for their work. And of course these systems are entirely opt-in, and they are not in the context of like copyright law enforcement. But the most important point is that the infrastructure that helps check attribution, check provenance, derivative works, licensing, identity, all these things are immediately available just because of the synergy of the Ethereum blockchain and basically content itself, so substance. So logic and substance. So you're asking like, yes. So you really don't want to lose your deposit. So the question was like whether there's ever a situation that I promised by giving a receipt to store your birth certificate, or like in particular probably a little chunk of that birth certificate for 10 years. But suddenly I'm lured into another arrangement because I got thrown at a lot of popular content which probably would serve me better. Is that what you're saying? In this case, obviously, that's why a promise has to be a promise. A promise means that even if there's a better circumstances coming to you, you still keep to your original promise. Otherwise, you stand to lose your deposit, and that should be a big enough disincentive. So yes, the answer is yes. We have to be very careful with the actual amounts, so that it will. No. So yeah. So in cases where you want extra value attached to your asset, like above, you want to insure it, so to say, above the disincentive that you get by the nodes potentially losing their deposit, then there are like explicit insurance schemes for that. So these will probably be third-party roles that take on the role of an insurer for your chunk, and they would probably in launch regular integrity audits. They would check whether your files are really available, and would only pay you kind of in installments. And these kind of systems are very nicely, easily programmable in Ethereum and these smart contracts. And you can also ask questions of Nick, if I think, if you have some.
One for you, last one for you. So as you have custodian nodes, and it's kind of like a sloppy distributed hash table. What are the guarantees inside the network if like a certain percentage of the nodes go down? You know, for example, those nodes made promises. Then do you have a method to offload the files that only those nodes, like only a few set of nodes now have, to the rest of the network, such that you still have assurances and guarantees?
Yes, we have to assure them against these situations with some redundant coding. So certain content has to be retrievable, even if parts of that are missing. So especially even if like a local area in the network is like it's completely cut off, we still have to be able to retrieve the content. And the standard solution for this is using erasure coding, which is like just a very basic idea that if you have error correcting code. So basically you inflate the coding of your data to a bigger data blob, which has the properties that any particular proportion of that data that you see is enough to reconstruct your original content. And if you distribute it in a redundant enough way, or these extra extended content, then you can make sure that your data is recoverable. Just also to say that please get close to the team, because obviously I have to mention that it's not only my work, it's a big team behind it, and so it's Daniel, it's Aaron, it's Nick, and Joet. So a lot of people from the Ethereum Foundation and the Halo of Ethersphere. So thank you very much to them as well.